Okay, so we're going to talk about something called enthalpy now, which is very similar to heat, but it tends to be a little confusing. Enthalpy is abbreviated as an H. It is also a state function, much like temperature. It is the amount of energy used or released in a chemical reaction or a chemical process. It's usually per mole of what they refer to as reaction. Okay, reactant and product. I'll show you what that means in a minute. There's all kinds of enthalpies. You're going to see delta H with RXN, with a VAP, SOLN, combustion. They're all done the same mathematically. It doesn't matter what they're called here, as long as they're called delta H. Okay, they are all calculated on a per mole basis, and it's usually heat per mole of reaction. So kilojoules divided by moles of reaction, which is a little weird looking. So it's used to calculate the amount of heat from a chemical reaction or process. If you're going to calculate from a heat from a temperature change, you want to use this equation. But if you're calculating heat from a chemical reaction, you're going to use stoichiometry, and I'll show you how that works. This usually is part of a stoichiometry calculation, but when enthalpy is given as part of a reaction, it's kilojoules per mole of reaction. So whatever you start with, you're going to convert into moles. So it could be a gas law, Pivner. You could be dealing with grams. You could be dealing with particles. You could be dealing with liters and molarity. Okay? It doesn't matter. Whatever you start with, you're going to change from moles of reactant. You're going to change it from the reactant into specifically 1 mole of reaction. So this is where you put the coefficient from the balanced equation. And then what you're going to do is you're going to use the enthalpy, which is kilojoules per mole of reaction, as a conversion. 1 mole of reaction produces heat. Okay, and I'll show you what I mean in a minute. So here's a balanced chemical equation. It's combustion of methane. The enthalpy of combustion is negative 890 kilojoules per mole of reaction. So to calculate the heat released when 8.9 grams of methane burns, start with the 8.90 grams, CH4, 16 grams, 1 mole, and then balanced equation, this is CH4. 1 mole of CH4 gives me 1 mole of reaction, and then 1 mole of reaction from here gives me negative 890 kilojoules. So all I'm going to do is do the math. And you get negative 495 kilojoules. Okay, not too bad. It's just another form of stoichiometry, that's all. So if I was going to do oxygen, and I'll show you how it's a little different with oxygen. 81.3 grams of oxygen. Change from grams into moles, just like always. But then, balanced equation, there are 2 moles of oxygen for 1 mole of reaction. And then 1 mole of the reaction is negative 890 kilojoules. So it's just a little bit different way of doing stoichiometry. You're still changing from moles of the reactant using the balanced equation, but you're always going to change it into 1 mole of the reaction. So if you did the math here, you get negative 1130 kilojoules. Now let's keep in mind that negative, all that means is it's exothermic. The magnitude of the heat is what you're concerned with mostly. Okay? So let's look at this one. So now I'm starting with heat. So if I have 515 kilojoules of heat, I'll put kilojoules on the bottom. That's where this number comes in, negative 1200 kilojoules for 1 mole of reaction. 1 mole of reaction gives me 1 mole of C3H8, balanced equation right here. And then 1 mole of C3H8 is 44 grams. Now you just do the math. Okay, let's do this one. I have 75 grams of methane, 185 grams of oxygen. This is a limiting reactant problem, so everything that's true for stoichiometry is true here. So C3H8, 44 grams, 1 C3H8, 1 reaction, 1 mole of reaction negative 1200 kilojoules. I'm going to do the same thing with the oxygen, then I'll solve them. But then in the oxygen, it has a coefficient of 5 for 1 mole of reaction. And then 1 mole of reaction is negative 1200 kilojoules. Oops, go back. I wasn't done there. Go back, go back, go back. Ah, I can't get to it. All right, so I figured it out. So it's negative 2045 kilojoules. And this one's negative 1387 kilojoules. Now, normally when we do limiting reactants, we always go with a smaller number. Well, since these are negative numbers, you might get a little confused, but let's remember that only means it's exothermic. So if we're doing the limiting reactant, we want the smaller magnitude. In this case, oxygen is the smaller magnitude because it's the limiting reactant. All right, so let's do it this way. And again, I have this value for the enthalpy of neutralization in here. It's an acid-base reaction. But what you need to do is you need to find the moles first. So liters times molarity gives you moles. So 0.125 liters. 1 liter is 4.25 moles. 2 HCl's give me 1 mole of reaction for my balanced equation. 1 mole of reaction is negative 56 kilojoules. I don't know what I just did. And I got negative 30 kilojoules. Okay, so once you turn it into moles, you're off doing the mole ratio, and it's always the coefficient to 1 mole of reaction, and this is delta H. And it doesn't matter what kind of delta H it is. So let's do this one. Okay, this is a combustion reaction, and it's negative 3940. Somehow it's missing from, it's up there. Anyhow, I have a gas, not at STP, so I have to do PIVNERT to find the moles, and is PV over RT is 1.5, 17.5 over R, and 298. And so once I find my moles, I get, once I have moles of oxygen, I'm going to go straight away into the stoichiometry. It's 25 oxygens for 1 mole of reaction. 1 mole of reaction is negative 3940 kilojoules. So it doesn't matter how you get the moles, as long as when you do the stoichiometry, you include the coefficient in the balanced equation. Okay, so let's go ahead and try this one. 67 grams of C3H8. So first thing I need is change that into moles. That's 44 grams. 1 C3H8 balanced equation is 1 mole of reaction. 1 mole of reaction is negative 1200 kilojoules. So I have about 1.5 moles-ish. That means I should get about 1.5 times the amount of heat. So I got, yeah, about that much. Negative 1827 kilojoules. Okay, so that's how much heat is being produced when it's burned. Okay, now if you assume all the heat is transferred to a container of water, now we're talking about a temperature change. And anytime it's a temperature change, Q equals MC delta T. Okay, so we're looking for mass of water. Could be raised from 25 to 90. So the specific heat is 4.18 joules over grams degrees C. Temperature change is 90 minus 25, 65. 65 degrees C. We're looking for the, We're going to solve for the mass, but we need to put in the heat value. Well, here is the heat, and this is exothermic because it's burning. It's a negative value. It tells me it's exothermic. So when I put it over here, this heat is being absorbed by the water. So I need to make sure it's positive. The other thing I want to pay attention to is my unit here is in joules. My unit here is in kilojoules. So 18.27123 to make it in joules. So you're going to get a pretty large mass. 6.724 grams. One thing I will tell you, if you leave it in kilojoules, what that means is your mass is going to be in kilograms. And it's fine as long as you acknowledge that. Okay? Either way is fine. Okay, so now I'm going to change the problem a little bit. You're going to have to calculate the enthalpy, and this is something you're actually going to do in the lab. So this is more appropriate to being prepared for the lab. When you're determining the enthalpy value using lab data, first thing you're going to do is determine the heat transferred, because there will be a temperature change. That means you're going to do this. Because you're using a small amount of whatever the reactant is, you're going to get relatively a small amount of heat. This is a lab. I can't give you a ton because I don't want you to generate tons of heat and melt stuff. Heat is a big deal when it comes to large amounts of chemicals. Enthalpy is the amount of heat generated per mole of reaction. So amount of heat, that's Q, per mole of reaction. Okay, and it's easiest to think of it in terms of proportions. So you calculate your heat transferred using Q based on the moles of reactant you have, and then you're going to use the coefficient of whatever your reactant is for 1 mole of reaction, and that will tell you the enthalpy in kilojoules per mole of reaction. And so it's easiest just to show you. So this is actually from the AP exam. They took a very small amount of glucose and it released 39 kilojoules. To determine the enthalpy of combustion, delta H, they want it, first of all, in kilojoules, and then they want it in moles of reaction. So let's do this. I had 39.0 kilojoules, and then I need to know how many moles of reactant I had in order to set up this proportion. So I'm going to do 2.50 grams. 1 mole of glucose is 180 grams. It is 0.0139. So that's my mole, 0.0139 moles. Balanced equation, I have 1 mole of C6H12O6 for 1 mole of reaction, and I want to know how many kilojoules that would be. Reaction. So I'm going to solve for that. Okay? First thing I want to point out, though, it says heat released by the reaction. That tells you that it's exothermic. If it's exothermic, you need to put in the negative. It's not going to do it for you. And then when I divide that out, do my mole ratio, it says negative 2806 kilojoules per mole of reaction. And that's the answer. Okay? So let's try the next one. So some NaOH is dissolved in water, gets hot. The temperature started at 20, temperature went up to 57. Anytime temperature changes, it's Q equals MC delta T. So to find the heat that was transferred, Q equals the mass. It says assume the specific heat of the solution is the same as water, so 4.18 joules over grams degrees C, and the temperature change is 37 degrees C. Okay, and here's my reaction. Now here's the important thing. We need to recognize what the mass is. Yes, there was 100 grams of water, but there was also a 62 gram sample of the NaOH, and both started at 20 degrees. And both ended at 57 degrees, which means the mass technically is 162 grams. And the only way to do this is to assume the specific heat is water, because most of the mass is water. And you get 25054 joules, because grams, degrees C, degrees C. Okay, now, first thing I want to point out, this is a positive value. because the temperature increased. And the temperature increased because it was an endothermic from the point of view of the water and the NaOH. Okay? It was endothermic from their point of view, but they got the heat from somewhere. Something gave them that heat. And so when we're doing enthalpy of solution, that's delta H. And that's always talking about the system or the process that caused the temperature change. Okay? Temperature change was here. This is a positive value. That means this process caused that. This process has a negative value. And they want it in kilojoules per mole of reaction. Okay, so I'm going to erase this and set it up again. So we have negative. I'm going to change this into kilojoules. 25.05 kilojoules. Negative because the process of enthalpy, dissolving the solution, is exothermic, and the water surrounding it took in the heat. The moles of reactant, I need to do that, 62 grams, 1 mole is 40, it's about 1.5, isn't it? Yeah, 1.55, 1.55 moles NaOH. I need to change it from moles of NaOH to moles of reaction. 1 mole of reaction in this balanced equation has 1 NaOH equals negative 16.2 kilojoules per mole of reaction. Okay, so a couple of things to watch for. Temperature change, you use that equation. To calculate heat, you include the mass of everything that changed temperature. But when you calculate the heat going to the enthalpy, you always change the sign because the heat is measuring the surroundings. The enthalpy is measuring the system. Okay, so let's do this one. I think this is the last one. I have an acid-base reaction. The temperature rises by 6.3 degrees. So again, Q equals MC delta T. Okay, assume the density of the solutions is 1 and the specific heat is the same as water. So limiting reactant, liters times molarity gives me moles. So I have 0.0453 liters times 0.1 moles per liter. 0.00453 moles of NaOH. Do the same thing for the acid. NaOH is my limiting reactant because it's a 1-to-1 ratio. Okay? To calculate the heat exchange, Q equals the mass, 45.3, 52.5. I can say that those volumes are the same as the mass because the density is 1. So my total mass is 97.8. I'm going to assume it has the same specific heat as water, and the temperature change was 6.3. Which means the heat is 2575 joules, and it is a positive value because the temperature went up. Temperature increases means it's endothermic, and that's the heat that was taken in by the surroundings. To find the enthalpy of neutralization, I'm going to take that heat in kilojoules, 2.575 kilojoules, for the moles of my limiting reactant. Because that limits how much heat I can get out of it. 1 NaOH for 1 mole of reaction. And I need to make this negative because this temperature went up. It is an endothermic process. It got the heat from my system, which is the reaction itself. and you get negative 568 kilojoules per mole of reaction.